This is Team Kickbutt. First is Nick Stone, our gear engineer. Then Owen Marnell, housing and shaft specialist. Next is JJ Lee, our mathematician. After that comes Davis Pike, logistics and project management. After that, Jackson Lewis, our second gear engineer. Finally, Garrett Lavin, he's our circuit dude. Over 750 million people across the world lack access to electricity. Energy access is directly linked to economic and educational opportunities, making this an extremely important obstacle to tackle. The objective is to provide easy-to-access energy and power generation without the use of established power sources. The team was tasked with developing a generator capable of powering an LED light for 5 to 10 minutes with 1 minute of cranking. The generator also had to be capable of trickle charging external batteries. Additionally, the generator must optimize power generation relative to size and weight, making it suitable for off-grid living applications. When it comes to objectives and design constraints, lightweight and size are a huge factor. Our generator must be able to fit inside of a backpack. It must also be easy to use in off-grid situations. It has to cost less than $250 to manufacture, and as previously mentioned, 1 minute of cranking must power an LED for at least 5 to 10 minutes. It must be capable of trickle charging external batteries, and has to have a user interface showing when charging is happening. This is our generator. When we open the lid, we'll see a 12-volt brushless DC motor. This allows us to take RPMs from the shaft side and output voltage to the breadboard. The breadboard has a voltage regulator. This prevents anything plugged into the generator from being damaged by a surplus amount of voltage. Additionally, there's a voltage readout, which tells us how much voltage is being produced by the generator. As we work our way around the generator, we'll first look inside. On the left side is the pole catcher. This acts as a ratchet gear mechanism that keeps the shaft from spinning in one direction and only spins in the other direction. This goes to a driving gear, which is fitted using a D profile and a pin. This goes to the second, and then third, and then flywheel, which is then fitted to the DC motor. As we continue our way around, there's a handle for improved ergonomics, our pull cord mounted on the outside, and a USB output. Our gear train is designed so that RPMs are maximized at the DC motor side. So as we spin, maximum torque is found at the input and minimum at the output. Here we have our voltage reader, a 7-segment display that displays how much voltage is being created by the generator, capping out at 5 volts because of the voltage regulator. There's the lit up LED that lights up as the generator is generating power, and finally a calculator shown charged, given by the power made from the generator. To show our trickle charging, here's Garrett. He's currently cranking the generator, and as you can see, there's a timer on the side showing how long he's been cranking. This next timer starts at around 30 seconds after Garrett has stopped cranking, and as you can see, the calculator is still charging. And then later, 6 minutes later, still not cranking, the calculator is still charging off of the power created by the generator. After analysis of the project, it was decided there were 4 major areas that needed improvement. First being the housing. Housing was effective but left room for improvement. To make the solution more portable and manufacturable, the housing could have been made smaller and more ergonomic. The second was torque reduction. Decreasing the gear ratio and the size of the gears will help minimize the amount of torque placed on the input shaft and increase the fatigue life of the generator. Third is user interface. Creating a user interface for users to be able to adjust generator settings and receive instant feedback on the voltage output. Finally is DFMA improvements. Developing a way to make the assembly of the housing easier and more efficient, such as making the system assemble on top rather than side to side. Going into the project, we had 5 main design goals. The first, converting mechanical power into useful electricity. Next, being able to run a built-in LED for 5 to 10 minutes off of 1 minute of cranking. Third, having user interface indicating power generation. Fourth, optimizing power generation relative to weight and size. And finally, being capable of trickle charging an external battery. After reflection on the project, we can happily say that we met all 5 of our design goals.